Hi everyone, welcome to lecture 6, and in these lectures we will cover the continuous random variables. We have studied discrete random variables so far, right? And we have some special distribution of that discrete random variables. If the discrete random variables in case, we can say that the range of possible values is a countable set. So the random variables will take values from that set. And that set, the values in that set can be enumerated and go through each value separately one by one. But those are not random variables, the discrete ones. Also, the continuous random variables are quite common. We can give some examples. For example, the velocity of a vehicle traveling along a highway, the level of water in a dense reservoir. So in this example, it is not possible to enumerate the random variables, right? It can take any values and it's not possible to enumerate them. You can extend these examples by yourself and see how the discrete random variables differ from the continuous random variables. That differentiation is important because there is a common mistake, that is a random variable which can assume the real numbers rather than the integers. Okay, so what I mean, you can think that the continuous random variables should take the real numbers, but that is not true. Okay, this is simply wrong. We don't say a random variable is continuous just because its range consists of real numbers. Okay, that's not true. So just remember the previous lectures. If the range is finite and it's countable, therefore the random variables would be discrete. But an infinite range consisting of the real numbers doesn't necessarily mean that we have continuous random variable. The following range, this range, is infinite, right? E to the x, where x in natural number, and the range will be e to the 0, e to the 1, e to the 2 until infinite. But we can still enumerate each values of these sets. So even though these sets consist of some rational numbers, they are not integer, because I can enumerate them, I can say that the random variables is discrete again. So how we can differ the continuous random variables and discrete random variables, we can easily say that if we can enumerate them, if we can count them, those will be the discrete random variables. On the contrary, if we cannot enumerate them, if they are not countables, so we can say these are the continuous random variable. So a random variable x is called continuous if there is a non-negative function fx, and that fx called the probability density function pdf of x, instead of probability mass function as we did in the discrete random variables, such that probability of x in B, the B is a set, will be equal to integration of f of x. Okay, and also in particular, we can specify the limits of that function like that. So the lower limit will be a and the upper limit will be b. So what does it mean? The probability of x, and x can take any value between a and b, and also a and b will be included, will be actually equal to the probability of a. The probability of x will be greater than or equal to a, and will be less than or equal to b. And this is equal to integration of f of x from a to b. Okay? So this can be interpreted as the area under the graph of PDF, right? Actually, this is the main logic of the integration. So remember that what is the basis of random variables? Actually, by using random variables, we map the sample space, right? So let's say this part, the events, and the random variables for this part, for this event, will take the values between A and B. Actually, that's mean if this is the graph of our sample space, that integration actually will that PDF will give us the area between A and B. So actually, I will calculate the area of this part. Okay, so this is the main base of PDF. So, but to calculate the area of anything, what I need width and height, right? To calculate calculate of any shape. So in other words, it can be it should be two dimensions, right? If there is a one dimension something like the line, the area will be zero, right? Because for this one I don't have height, or if that is the case, in this case I will not have the width, so I cannot calculate the area. So from this point, let's say let's calculate the probability of x is equal to a, and that's mean the probability of x in from a to a, just some specific points. So what will be the area of what will be the area between these limits? It will be zero, right? Because let's say there's something like that, that's the graph, and that is the A point. So I have height, but I don't have the width. So that's why I cannot calculate the area of this line in the point A. Okay. So if this is the case, that will be the probability of x will be greater than or equal to A and will be less than or equal to B, actually is equal to the probability of x will be greater than A and will be less than B, or it will be probability of x will be greater than or equal to A and will be less than B, and vice versa. So that's mean the including or the excluding the endpoints of an interval will not affect its probability. And in this case, the probability is the area between that limits. Okay, so all this term will be the same. So to qualify as a PDF, a function should be a non-negative. We said that. And also, the qualify as PDF, which is the normalization axioms of the probability, a function should have the normalization property. So that means sum of all possible values, or in other words, the probabilities of all possible values should be equal to 1. So if you think from the area, the calculating area point of view, so if that is the function, the area under that function, the whole area under that function should be equal to 1. So if that is the case, we can say that PDF is a proper one. So let's say we have specified an interval, like for an interval, the lower limit will be x, and the upper limit will be x plus delta, and delta says real small number. Okay. So in this case, the probability of x, and x plus delta actually will be the integration of f of x from x to x plus delta, right? And it will be approximately f of x times delta y. So let's say this is the point x, and this line, the y line, is the PDF of x, and this part is the delta. How can I calculate the area of this part? It's simply the height times width, right? What's my height here? Is something here, right? And this is the value of f of x. So the height will be f of x, and what is the width? It will be the delta, right? So that's why the integration of f of x for those limits will be approximately equal to f of x times delta, and this is called the probability mass per unit length near x. Okay, and this is a cool example to understand the basis of integration and the basis of the probability of the continuous variables. Okay, please note that a PDF can take arbitrarily large values, and it still can be a valid, a proper PDF. So to make it more concrete, assume that we are given a random variable x with the PDF, this one. So if x is between 0 and 1, the PDF value, or in other words, the probability of the specific values, will be calculated as 1/2 times square root of x. Otherwise, it will be 0. So if that is the proper one, that's mean, let's say this is something like that, the shape of the graph of that function, and so between the area between these limits should be equal to 1. Okay, so in other words, if I calculate all possible probability mass per unit length, and if I sum all of them, I should get 1. Okay, so let's say let's calculate the area between that PDF. Okay, so we have to look first the integration of f of x from -infinity to infinity, but this function is valid only in this range. Okay, so we can think that function as 3 parts. In the first part, the x will be less than 0, and in the third part, x will be greater than 1. And in these 2 parts, the function will not be valid. The only value it can take in those 2 parts is 0, but in the middle part, we have some function. Okay, so that's why this is equal to the integration of f of x from 0 to 1, because this function is only valid between these limits. So if you take the integration of this one, I hope you remember that one, we can simply write this one as 1, and let's say this is a 1 x this one, and which is equal to, sorry, this one, not -1, and this is equal to x 1, and which is equal to 1/2 times x divided by 4. Let's say this is the upper limit and this is the lower limit. So these guys will be, this part will be 2 square root of x, and this will come here and they will cancel each other, and I will get the square root of x. Okay, so what is my limits? It's from 0 to 1, so it will be equal to minus this one, and it will be the 1. So the area under those function between those limits will be equal to 1. That's why even that gets really large numbers, and that PDF can be a proper one. So when this function gets an arbitrarily large number, so let's look at the graph of that function. So if the value of x is less than 0 or greater than 1, it can the f of x will be 0, right? So there is no valid function in those parts, less than 0 and greater than 1. But the function is valid in this range. If x takes the value, any value between 0 and 1, we have a proper or a valid function. And if x is if x approaches to 0 as close as possible, the value of x will be arbitrarily large, okay? But even though this is the case, still f of x is a proper PDF because it satisfies the normalization the normalization axioms of the probabilities. Okay, so I don't think if a PDF gets a really large number, so it is not a proper the PDF. This is not true. Even if it gets arbitrarily large values, it still can be a valid, a proper PDF.